Today I want to finish up the section on Hamiltonian mechanics, and this will just be this sort of standard way of thinking of Hamiltonian mechanics. And then next time we'll give the formulation in terms of symplectic geometry. So just by way of completing what I need to say here, you will recall that the last time we left off, we had derived the Hamiltonian equations of motion. And they basically said that if I had some Hamiltonian, which was related to the Lagrangian of the system by a Legendre transformation, then whereas the Lagrangian was a function of the generalized positions and the generalized velocities, q and q dot, the Hamiltonian was a function of the generalized coordinates, q, and the generalized momenta, p, of the system. In which case, the Hamiltonian equations of motion were two first-order equations that read q dot was dh by dp, and p dot was minus dh by dq. And my statement was that this set of first-order equations encoded the same information as the second-order Euler-Lagrange equations, but were sometimes easier to work with, and certainly if you're interested in quantum mechanics. Typically, quantum systems are easier to specify in terms of the Hamiltonian and the Hamiltonian evolution than the Lagrangian of the system. Okay, so what I want to show you today is basically rounding up the way that we, in modern terms, think of Hamiltonian mechanics. It's not entirely modern. It goes back to I guess, turn of the 20th century, but it's certainly a lot more modern than Newton was thinking about it. And then I'm going to finish off this lecture. So I'm going to start off with an example of the harmonic oscillator, and I'll show you what the Hamiltonian equations of motion look like for the harmonic oscillator. And then I want to introduce the idea of a Poisson bracket between two variables and show you how we can reformulate the Hamiltonian equations in terms of the Poisson bracket. And this is particularly neat because, as Dirac envisaged it, the transition from classical to quantum mechanics involves merely replacing, I say merely, obviously there's a lot more that goes into it, but at a superficial level, it involves replacing the Poisson bracket with a commutator and the variables that we work with operators. So that's where we are right now. And then I'm going to finish off the lecture by talking about a very important result called Noether's theorem, which relates symmetries of a system to conserve quantities. So let me start then by just reminding you about the Hamiltonian equations of motion. And this is the statement that q dot is dh by dp and p dot is minus dh by dq. Again, these are first order equations. These are first order equations that encode the same information as the second order Euler-Lagrange equations. So let's do an example quickly to illustrate this and maybe draw some comparisons with what you might be familiar with from Lagrangian mechanics. So given a Lagrangian for a one-dimensional harmonic oscillator, so a one-dimensional harmonic oscillator has dynamics encoded in the Lagrangian L of Q dot. Let's say we're talking about a single oscillator. And this is a half the mass of the oscillator times its velocity squared. So this is just the kinetic energy, if you want, minus a half m omega squared q squared. So this is the kinetic energy. And this is the potential energy. Of the oscillator. And this omega here is its natural frequency. Q is, of course, the position of the oscillator, and Q dot is the velocity of the oscillator. So, okay. So if you take this equation, you take this Lagrangian and you plug it into the Euler-Lagrange equations, you'll get the second order harmonic oscillator equations, which basically tells us that the force exerted on this harmonic oscillator is the Hooke's law restorative force, that if you push the harmonic oscillator in this direction, the restoring force acts in that direction, and it's proportional to the displacement of the object of the mass from its equilibrium position. So you can think about a pendulum executing small angle oscillations. That's harmonic oscillator oscillations. And by now you probably all appreciate that the harmonic oscillator is the canonical system from which we learn a lot of the mathematics and physics that we work with in other systems. So let's take this and see what the Hamilton equations of motion look like for the harmonic oscillator. So first things first is we need to calculate the momentum that's conjugate to Q. So the conjugate momentum is P, and P is dL by dQ dot, which is the partial derivative of this Lagrangian with respect to Q dot. There's no Q dot dependence here, so the derivative there is 0. And the Q dot dependence here is only quadratic, so this is just mQ dot. So the momentum is the mass times the velocity, as you've learned from high school already, which means that Q dot can be traded in wherever I see it for the momentum of the oscillator divided by its mass. Okay, so that means that if I want to reformulate things in terms of the Hamiltonian, I have to replace Q dot everywhere I see it by the momentum of the oscillator divided by its mass. So directly substituting into the Legendre transformation, then we find that the Hamiltonian is, remember, PQ dot minus L. I don't have any sum in this because there's only one variable, Q. PQ dot, Q dot was P over M, so this is just P squared over M minus a half P squared over M plus a half M omega squared Q squared, which is just P squared over 2M plus a half M omega squared Q squared. So again, this is the kinetic energy, and this is the potential energy, and the difference between the Lagrangian and the Hamiltonian is this sign here. So where the Lagrangian is the difference between the kinetic energy and the potential energy, the Hamiltonian is the sum of the kinetic energy and potential energy. So in this way, the Hamiltonian corresponds to the total energy of the oscillator. The associated Hamiltonian's equations, so Hamilton's equations are that P dot is minus dH by dq. dH by dq is m omega squared q. So this is minus m omega squared q. And q dot was plus dH by dP. And dH by dP is just P over M. And you can see that if you take derivatives of, let's say, the second equation and substitute the first equation into it, you will get precisely the statement that Q double dot is minus M minus omega squared Q, which is nothing but the second order equations for the harmonic oscillator. Okay, any questions? No. Okay. So this is what I wanted to say about just reformulating Lagrangian mechanics into Hamiltonian mechanics. But there's actually a little bit more that we could do. To do this, let's think a little bit about phase space again. So remember, phase space was the space of momenta, the space coordinatized phrases. Phase space was a manifold coordinatized by the generalized momenta and the generalized positions, right? So given an n-dimensional system, so a system with n degrees of freedom, sorry, I should say that precisely, given a system with n degrees of freedom, for example, n oscillators, the phase space of that system is a 2n dimensional space, which consists of the n coordinates that are the generalized coordinates and n coordinates that are the generalized momenta. So in total, giving me 2n coordinates. So it's a 2n dimensional space associated to the system with n degrees of freedom. So suppose I now have two functions, let's say a and b, and these are both functions on the phase space of a given Hamiltonian. So let a of q and p and b of q and p be functions on the phase space of the Hamiltonian H. Okay. Now I want to define a new object called the Poisson bracket. The Poisson bracket is defined as follows. The Poisson bracket between A and B is written like this. Again, it depends on the literature that you're reading. Sometimes people use square brackets with a little PB below it. Sometimes people use square brackets, and it's clear from the context. More generally, people tend to use curly brackets. So A curly brackets B is defined to be the sum over I of dA by dq I dB by dP I minus dA by dPi dB by dQi. All right, so this is the Poisson bracket, and it's going to play a central role in what we have to say going forward. Specifically, the formulation of classical mechanics in terms of the geometrical language that we're building, but also we're going to be making some small forays into the quantum realm, and this Poisson bracket will be crucial there. So let's see what some of the properties of the Poisson bracket are, and then I'll show you why I want to introduce it in the first place. So some of the properties of the Poisson bracket are as follows. Clearly, by construction, by which I mean this minus sign here, the Poisson bracket is skew symmetric. So skew symmetry is 1. In other words, A bracket B is minus B bracket A. The next thing that's easy enough to show, is essentially using the linear property of the partial derivative, is that the Poisson bracket is linear. By which I mean A bracket C1 B1 plus C2 B2. Obviously, this extends to n objects, is C1 A bracket B1 plus C2 A bracket B2. Both of these things are quite straightforward to show. The third thing is what we were calling the Leibniz property. It's a little bit more painful to show. However, it's not that much more painful to show because we know that the partial derivative that goes into the definition of the Poisson bracket is an actual derivative, so it satisfies the product rule. And you can use this to show that A bracket BC is B times A bracket C plus A bracket B times C. Of course, because we're talking about functions here, whether I put the B on the left or the right, or the C or the left or the right of the bracket, doesn't really make a difference. I chose to write it this way because in the transition between classical and quantum mechanics, when you replace the Poisson bracket with commutators of operators in general don't commute, in which case the correct way to state the Leibniz property of the Lie bracket of operators is in this form. The final property that we need to state right now is also not conceptually difficult to show, but it's a bit of a pain in the butt. And I'm going to leave all of these for you to show, because it's a character building exercise. You should all do it once. And this is the fact that the Poisson bracket satisfies the Jacobi identity. And the Jacobi identity for the Poisson bracket basically says that given three functions, A, B, and C on phase space, that the commutator of the commutator, the Poisson bracket of the Poisson bracket between A and B and C, like such, plus cyclic permutations, in other words, C, A, B, plus B, C, A, vanishes. Right, so that's a Jacobi identity. I would like you to spend a little bit of time and prove all of these relations. They're a good experience to show that this is what the Poisson bracket satisfies, and they're a good experience to work with the properties of the Poisson bracket, right? Of all the possible Poisson brackets that we could write down, there are three that are fundamental. And those are the ones that involve the specific functions Qi and Pi respectively. So let's list them as separate properties. So property 5 says that Pi, Pj is the same as Qi and Qj, and that's 0. And I'll do this one for you. Qi, Poisson bracket with Pj, is, by its definition, sum over K, say, dqi by dqk, dpj by dpk, minus dqi by dpk, dpj by dqk, which is sum over k of of delta ik delta jk, which is delta ij. So these three fundamental Poisson brackets, if you want, tell us that the brackets between momenta vanish, the brackets between positions vanish, and the brackets between positions and momenta are delta ij. Okay. So why would we need to introduce the Poisson bracket at all? To see why this is a useful thing to know, let's note the following. Suppose I have some phase space function. And I'll call it A. So A of Q and P is some function on phase space. And this is the phase space of the Hamiltonian H. Okay. The question that we have is, what is the time evolution of A? So how does A evolve in time? So we need to calculate dA by dt. Okay, so this is for some arbitrary function on the phase space. So we ask, what is dA by dt? Well, suppose that A is a function of actually k of these q's and k of the p's. So then dA by, just to do things in generality, so the sum over k of dA by dqk, dqk by dt. So each of the qk's is a function of time only, therefore I can take a total derivative, plus dA by dpk, dpk by dt. So this is just a chain rule. The A is a function of the QKs, the QKs of the QKs and the PKs. The QKs and the PKs are functions of time. So that's what I get from there. These two things, Q dot and P dot, we get from Hamilton's equations. So Q dot, I remind you, Hamilton's equation tells me that Q dot is dH by dP, and P dot is minus dH by dQ. So this is equal to the sum over K of dA by dQk, dH by dPk, minus dA by dPk dH by dqk from the Hamiltonian equations of motion. But this is nothing but the Poisson bracket between A and H. In other words, what we've learned is that the time evolution of some function on phase space, dA by dt, is nothing but the Poisson bracket between that function and the Hamiltonian. So again, for those of you who've done quantum mechanics, this should be, the structure of this should be entirely familiar. This is what we call the Heisenberg equations of motion, which tell us how an operator on the Hilbert space evolves by commuting with the by the commutation relation between that operator and the Hamiltonian of the system. Any questions? So I hope you're kind of seeing how all of these things tie together if you haven't seen them before. So now we have a new way of writing down Hamilton's equations of motion. And they basically tell us that dpk by dt is pk commutator with, Poisson bracket with h, and dqk by dt is qk Poisson bracket with h. So that's neat. We've taken these equations and we formulated in terms of the Poisson bracket between the generalized coordinates and generalized momenta and the Hamiltonian. And what we'll see just now in the next lecture is how this shapes our thinking about the geometrical formulation of classical mechanics. But it also gives us a nice way of thinking about conserved quantities. So a conserved quantity is one which does not evolve in time. In other words, if A is a conserved quantity on phase space, then dA by dt is equal to 0. But if dA by dt is equal to 0, that means that A Poisson bracket with H, with the Hamiltonian, must necessarily vanish. Again, in the quantum mechanics setting, we would say that we have a conserved quantity on our hands if that quantity commutes with the Hamiltonian. Okay, so this is nothing but the classical analog of those statements that you might be familiar with already. So let me write this down. A conserved quantity let's say A of Q and P is one for which dA by dt is a Poisson bracket with H, and that's equal to 0. So if I find a quantity in phase space such that its Poisson bracket with the Hamiltonian associated to that phase space vanishes, then I know that that quantity is a conserved quantity. Okay. And by conserved quantity, I mean things like momentum or energy, etc. So all of these quantities, all of these functions of the variables on phase space satisfy the property that their Poisson bracket with the Hamiltonian of that system vanishes. And this leads us to, any questions at this point? Is everybody happy with this? Great. So this leads us to one of the deepest results, if you want, in theoretical physics, in my opinion. which is the statement called Noether's theorem. And Noether's theorem was formulated by Emmy Noether when she was trying to understand essentially conserved energy in general relativity. So in 1916, Einstein writes down his general theory of relativity. About 2 years after David Hilbert had been playing around with these ideas in a more mathematical treatment in Göttingen, and Hilbert realized pretty much as soon as Einstein had formulated general relativity, kind of physicist's way of thinking about it, that there was a problem with this theory in that it didn't seem to conserve energy. And if it didn't conserve energy, then there's something fundamentally weird about the theory. So he brought in Emmy Noether, who was a prodigal mathematician, but being a woman, was not allowed to teach mathematics. So she taught at Göttingen under the guise of David Hilbert until the Nazis came along and she was forced to leave the position. Well, she was forced to leave what little position she had. And Noether took a look at the problem of trying to understand how energy was conserved in Einstein's theory of general relativity, and realized that there was actually a more general statement to be made, and that more general statement we now call Noether's theorem. And Noether's theorem is basically the statement that encodes the relationship between symmetries in a physical system and conserved quantities. Okay, so what I want to show you here is how the Hamiltonian formulation of the problem actually gives us a really nice way of not only thinking about this relationship between symmetries and conserved quantities, but it actually gives us a construction of the conserved quantity associated to a particular symmetry. So let's state Noether's theorem, and I'll prove it to you, and I'll show you what the conserved quantity looks like. So Noether's theorem encodes the relationship between conserved quantities and just to remind you, conserved quantity is any quantity that satisfies this property, and symmetries of a physical system. So let's see what that means more precisely. So suppose I have some Hamiltonian, H. So suppose H of QK and PK is a Hamiltonian. And I want to assume that this Hamiltonian is invariant under coordinate transformation. So let's just work with infinitesimal transformations. So I'm going to assume that H of QK PK is invariant under the infinitesimal transformation of coordinates QK to QK prime, and QK prime is going to be QK plus epsilon, some small epsilon, phi k. And phi k in general is a function of the q's. Okay, so what does it mean for QK to be invariant? Well, when I make this change of coordinates from Q to Q prime, it induces a change in the associated momenta. Remember, the momenta, the conjugate momenta to Q's, they're conjugate variables to Q's. So they are derived from the Q's, or they're derived from the Lagrangian by taking the Lagrangian taking the derivative of the Lagrangian with respect to q dot. So making a change of coordinates from q to q prime induces the change of in the momenta from, let's say, p to p prime. What it means to say that the Hamiltonian is invariant is that h of q p is the same as h of q prime and p prime. I'm dropping the dependence on the k. We understand that it's there. Well, this is a change of coordinates, right? So it comes necessarily with a Jacobian. The Jacobian of the change of coordinates is, so the Jacobian of the transformation is given by, I'm going to call it lambda ij, and lambda ij is dqi prime by dqj. And you can calculate this, you should calculate this and show that it's just delta ij plus epsilon d phi I by dqj plus things that are of order epsilon squared. Well, we're only interested in the lowest order in epsilon, so we're going to drop this piece. In fact, let me put it there and then scratch it out just to show you that it's there. Okay. Under this change of coordinates, the momentum transforms as follows. The induced change in momentum is Pi going to Pi prime, and this is the sum over J P J, say lambda J I inverse, which is Pi minus epsilon sum over J of P J d phi J by dq I. Okay, so that's what the change in momentum is. So let's see what this invariance of the Hamiltonian means. So the invariance of the Hamiltonian means that if I take h of qk prime pk prime minus h of qk pk, then I ought to get 0, right? But I also know that the chain rule applies to h, and I can ask what is h of the primed variables in terms of the unprimed variables, and this is just dh by dqk delta qk plus dh by dpk delta pk. It's actually h of qk pk plus this stuff here, but then I'm subtracting off an h of pk qk as well, so it's just this, and this is dh by dqk delta QK, the change in QK, is precisely what we were calling epsilon phi of k. That's QK plus the change in QK, the infinitesimal change. I've just coded the infinitesimal change like this. So this is epsilon phi k minus dH by dpk. And the infinitesimal change in the momentum is this stuff here. So let me use Einstein notation here and drop the explicit sum on J. So this will just be epsilon times pi d phi I by dq k. And I can take out an epsilon from this. And then I realized that what's left, in other words, the dH by dq times phi k minus dH by dp times pi d phi I by dqk is nothing but the Poisson bracket of H with some quantity that I'm going to call Q, and that quantity Q is the sum over K over I, say, of pi phi I of Q. And then given what we've just said, this is nothing but epsilon dq by dt. Up to a minus sign, sorry. Let me just fix that. So let's see. If we take a step back and ask, what have we done? We've made an infinitesimal change to the coordinate q. And this change has been such that it has left the Hamiltonian, remember, which codes all of the dynamics of the system, invariant. In other words, this coordinate change is a symmetry of the system. We've made a change to the system and it's left the system invariant. So it's a symmetry of this Hamiltonian system, okay? And the symmetry of this Hamiltonian system has left the Hamiltonian invariant, but it's also given rise to a quantity that is conserved. dq by dt is equal to 0. What is that quantity? That quantity is the sum over I of the ith momentum coordinate multiplied by phi I. Phi I, remember, was the thing that defines for us the coordinate transformation. In other words, finding a conservative, in other words, Noether's theorem tells us that finding a conserved quantity in a Hamiltonian system is the same as finding a transformation that leaves that Hamiltonian invariant, with Q here playing the role of the generator of that transformation. So this allows us to make a statement of Noether's theorem. So finding a conserved quantity is equivalent to finding a transformation that leaves the Hamiltonian invariant and the conserved quantity Q is the generator of that transformation. In other words, Noether gave a constructive proof that to each symmetry in a Hamiltonian system, there must exist a conserved quantity that is the generator of that symmetry. Okay, so she told us that we can associate to each conserved quantity a symmetry and vice versa. And she also told us how to find that conserved quantity. Okay, so I'm going to stop here for today. And I'm going to